Hello, today we are going to start a new module which is the micromechanics of lamina. So, today is the first lecture of this module. So, let us first understand the background and significance of the micromechanics of lamina. What is the importance of studying this micromechanics of lamina? Now, a lamina as we understand that it actually consists of it is a heterogeneous material. Okay? It consists of fibers and the matrix. Okay? Therefore, the mechanics of lamina could actually be studied in two different scales, okay? Namely the macromechanics of lamina and micromechanics of lamina. So, in our previous module we have actually studied the macromechanics in details, wherein a lamina is actually represented by means of its average properties, that means average elastic constants and average strength properties, and we understood how to develop the stress strain relationship based on those average stiffnesses, as well as the we have also developed the strength failure theories based on the average strength properties. Okay. But we have never in macromechanics of lamina, the interactions of the fiber and the matrix have never been addressed. Okay. So, in micromechanics these interactions of fiber and the matrix is actually taken into account. Okay. So, suppose in macromechanical analysis we have duly considered the direction dependencies of the strength and the stiffnesses, but one important questions that how these strengths and the stiffnesses of a lamina are influenced by the corresponding strengths and stiffnesses of the constituents, that means the fiber and the matrix is actually not answered, we have not discussed. So, in micromechanics this is actually addressed, that means in micromechanics we try to develop some estimate, we try to estimate the properties of a lamina in terms of the properties of the constituent fibers and the matrix. For example, suppose in macromechanics we can have a say glass epoxy lamina, where say the glass fibers are 60% and 40% is epoxy. We can take that lamina and we can test it in a uniaxial tensile testing, and we can find out that what is the stresses and what are the stresses and strains. Plotting the stresses and strains, we can determine the Young's modulus, that is the longitudinal Young's modulus, and we can also determine what is the longitudinal tensile strength of the particular lamina. Now, that is true for a given lamina where the percentage of glass is 60%, percentage of epoxy is 40%. Suppose we want to know if the relative proportions are different, that means suppose the glass fiber percentage is say 60%, say 70% and the epoxy percent is 30%. What we do? Well, we can again make another lamina, test it and get the longitudinal Young's modulus as well as the ultimate tensile strength. Therefore, for each different relative proportions of the constituents we can actually measure, but this is time consuming. Similarly, we can do for the other properties also. Okay. Now, this therefore, in micromechanical analysis we actually try to develop certain procedures through which we try to actually achieve we try to develop certain relations by which we can find out, we can determine the properties of lamina in terms of the properties of the fibers and the matrix and their relative proportions. Okay. Now, what we do with these properties? These properties are subsequently used for the macromechanical analysis of the laminate. Okay. Therefore, in a way these micromechanical procedures actually aid the macromechanical analysis of composites. Now, one thing important to note in this micromechanical analysis of lamina, this micromechanical study has nothing to do with that the study at the molecular level or at the micro level. It is actually just to distinguish between the macromechanical analysis where the interactions of the fibers and the matrix are actually not considered, but in micromechanical analysis of lamina these interactions are considered. That is all about the micromechanical analysis. It has nothing to do with the that it is at the micromechanical scales. Okay. Now, when these relationships in micromechanical procedures are actually developed and the relations by which we can determine the properties of a lamina in terms of the fiber and matrix properties. Now, how the efficacies of those established relations are actually decided by how well those predicted properties do agree with the experimentally measured values of those corresponding properties. Okay. Now, given the fact that there are key assumptions which are actually made in micromechanical analysis, say for example, that perfect bonding, we always assume there is a perfect bonding between the fibers and the matrix. Okay. Also it is assumed that the matrix are void free. So, these assumptions many times do not match with the actual lamina which is tested, and therefore, put limitations on the micromechanical predictions. Therefore, before using these micromechanical procedures for design and analysis of composite laminates, they should be carefully validated with the experimentally measured values, then only those relations could be actually used with confidence. With reference to an orthotropic lamina, we have 4 elastic moduli. What are those? 4 engineering constants are E1, that means longitudinal Young's modulus, E2, that is transverse Young's modulus, nu12, that is in plane Poisson's ratio, and G12, that is the shear modulus, that is with respect to an orthotropic lamina, where 1 and 2 are the principal material directions. Similarly, we have 5 strength parameters. What are those strength parameters? The strength parameters for an orthotropic lamina are, because of their direction dependency, there is longitudinal tensile strength sigma Tu, longitudinal compression strength sigma 1 Cu, transverse tensile strength sigma 2 Tu, then transverse compression strength sigma 2 Cu, and in plane shear strength tau 1 to U. Okay. They are not equal because the strengths are also direction dependent. Therefore, we have 5 strength parameters. Then we have 2 coefficients of thermal expansions. We have studied these things in details in the macromechanical analysis, that is coefficient of thermal expansion, that is longitudinal coefficient of thermal expansion alpha 1 and transverse coefficient of thermal expansion as alpha 2. Then we have 2 coefficients of moisture expansion, 2 coefficients of moisture expansion, that is beta 1 is the longitudinal coefficient of moisture expansion, beta 2 is the transverse coefficient of moisture expansion, this is expansion. Okay. Okay. So, altogether there are 13 parameters. Okay. Altogether there are 13 parameters in an orthotropic lamina, unidirectional orthotropic lamina. Out of that 4 engineering constants, 5 strength parameters, 2 coefficients of thermal expansions and 2 coefficients of moisture expansions. Now, these 13 parameters could actually be determined by conducting some tests like compression, tension, hygroscopic test, thermal tests, and we can obtain those parameters. These are all average properties of a orthotropic lamina. Now, the fact that these parameters are actually functions of several variables, such as the corresponding properties of the fibers and the matrix and the relative proportions. That means, say for example, the longitudinal Young's modulus E1 of the lamina is definitely influenced by the Young's modulus of the fiber, Young's modulus of the matrix, and the relative proportions. If the fiber volume fraction, if the fiber is 50% and matrix is 50%, we will get some value of longitudinal Young's modulus. Suppose the fiber is 60% and the matrix is 40%, there will be some other value. Therefore, similarly for all such properties, say for example, the coefficient of thermal expansion alpha 1 of the lamina is decided by what is the coefficient of thermal expansion of the fiber, what is the coefficient of thermal expansion of the matrix, and what are their relative proportions. So, all these 13 parameters are functions of several variables. Now, as we have discussed already, we can determine these parameters by conducting experiments, but experiments are actually expensive and time consuming, especially more so in the case of orthotropic lamina like unidirectional lamina, orthotropic lamina, because there are number of parameters are more, say unlike isotropic materials where we have 2 engineering constants, Young's modulus and Poisson's ratio, and we have 2 strength parameters, that means tensile strength and shear strength. In some cases where tensile and compression strengths are different, 3 strength parameters, but here in the case of an orthotropic material we need 4 engineering constants E1, E2, Nu1, G12 and 5 strength parameters already discussed. In addition, and then we need 2 coefficients of thermal expansions and 2 coefficients of moisture expansions. So, determination of all these 13 parameters by conducting experiments, and that too when the relative proportions of the constituents change is actually time consuming and expensive. Therefore, it is always desirable to have a reliable prediction method, so that we could find out or we could determine the properties of a lamina in terms of the properties of its constituents and the relative proportions. So, that is where the justification of studying the micromechanical analysis, wherein the objective is actually to develop a relationship. We have written here that P C is as a function of P F, P M, V F, V M, S and A, where P stands for P C stands for properties of the composites. This could be the stiffnesses, that means E1, E2, Nu12, G12, then sigma 1 Tu strength parameters, like this, all these 13 parameters. And similarly, Pf is those for fibers, those, that means say Pf is the maybe the Young's modulus of the fiber, Poisson's ratio of the fiber, shear modulus of the fiber, strength of the fiber, and Pm are those for the matrix. These are for fibers, these are for matrix. S is the shape parameters and A is the arrangement, that means how the what is the shape of the fibers. Shape of the fibers may be circular or it may be some other shapes, then A is how they are arranged, regularly spaced or not. So, as a function of these constituent properties, and this Vf, Vm are the volume fraction of the fiber, Vm is the volume fraction of the matrix, that means the relative proportions. So, the objectives of the micromechanical analysis is actually to develop a relationship where we try to propose a relationship where the properties of the lamina could actually be obtained as a function of the corresponding properties of the fiber and the matrix and the relative proportions. Okay. Now, in micromechanical analysis there are several approaches, okay. Objective remaining the same, there are several approaches like mechanics of material approach, then numerical approach, then elasticity approach, variational approach and semi empirical methods. Okay. Now, in mechanics of material approach is based on simplified assumptions of uniform stresses and strains. Okay. It is observed that this mechanics of material approach, they are simple and it is reported and it is observed that they actually provide a good estimate of the longitudinal properties, whereas they do not provide they do not agree well with the experimentally measured values for transverse properties. The numerical methods like finite element method, finite difference methods or boundary element methods provide a very good predictions of the properties of lamina in terms of the properties of the fiber and the matrix. However, they do not provide any closed form solutions, and therefore, for each specific case we have to run separate numerical simulation, and it is also time consuming. Okay. Then elasticity methods or approaches are actually based on the classical theory of elasticity, where the equations of equilibrium, compatibility conditions and the boundary conditions are used to arrive at a closed form solution. Okay. However, the geometry is simplified assumptions are made in terms of geometry, and therefore, sometimes important interactions between the fibers and the matrix are not considered, and they do not agree well with the experimentally measured values. Okay. Then variational approach is based on the energy principle, like principle of minimum potential energy, and it provides upper and lower bounds on the properties of the lamina. Then we have semi empirical methods. There are a number of semi empirical relations are provided, and one of the important and very well correlated is Halpinshine method, which actually overcomes some of the drawbacks or limitations of the theoretical approaches just now we have discussed. So, Halpinshine method is many a times used to predict the properties of a lamina in terms of the properties of the fibers and the matrix, and it correlates better with experimental results compared to the theoretical approaches. Some of the important terminologies and notations which we will be using throughout this micromechanical analysis: small w stands for the mass of the composite, a suffix c for composite, f for matrix, and m for small w is the mass of the composite, suffix c stands for composite, and suffix f stands for mass of fiber, and similarly Wm stands for mass of the matrix. Small v represents the volume, and similarly Vc is the volume of the composite, Vf is the volume of the fiber, and Vm is the volume of the matrix, and rho as usual stands for the density. So, rho c, rho f and rho m are the densities of the composite, fiber and the matrix respectively. Then fiber volume fraction is the ratio of the volume of fiber to the volume of the composite. Okay. So, and similarly the matrix volume fraction Vm is the ratio of the volume of the matrix to the volume of the composites, and naturally the maximum value of Vf could be 1 and the minimum value could be 0. If all fibers, then Vf is 1, if all matrix, then Vm is 1, and total volume of the composite Vc is nothing but the volume of the fiber and the volume of the matrix. Of course, we make a here we make the assumption is that the composite consists of fibers and matrix only, and there is no void. Therefore, Vc is equal to Vf plus Vm, and naturally the volume fraction Vf plus volume fraction Vf must be equal to 1. Okay. So, sometimes the relative proportions of the fibers and the matrix are also expressed in terms of the mass fraction or weight fraction. So, analogous to volume fraction, the mass fraction of fiber capital W f is the ratio of the mass of the fiber to the mass of the composite. Similarly, the mass fraction of the matrix capital W m is the ratio of the mass of the matrix to mass of the composites, and the total mass of the composite is the sum of the mass of the fiber and the mass of the matrix, and therefore, analogous to volume fraction, the mass fraction of the fiber and matrix adding together must be equal to 1. Okay. So, there we could develop the relationship between the mass fraction and volume fraction in terms of density. So, going by the definition of density, so rho c is the density of the composite, mass per unit volume. Similarly, rho m is the density of the matrix, mass of the matrix by volume of the matrix. Similarly, rho f is the density of the fiber. So, using the definition of mass fraction, W f could be written as small w f by W c, and writing this mass in terms of volume and density, we arrive at this, that mass fraction capital W f is equal to rho f by rho c into V f. Okay. So, we could obtain the relationship between the mass fraction and the volume fraction, okay, which is sometimes important. Okay. Sometimes we need to express the weight percentage of the constituents, and if we know the volume fraction and the volume percentage, then we can determine the mass fraction of the constituents. And using this relation, we can write down the we can obtain a relation of the density of the composite in terms of density of the fiber and density of the matrix as rho c is equal to rho f V f plus rho m V m, and in terms of mass fraction we could obtain the relation that 1 by rho c is equal to W f by rho f plus W m by rho m. Now, we may in micromechanical analysis, it is assumed that there is no void, but suppose there is a void. Okay. The presence of void, how the void could be there, because of the manufacturing inaccuracies, sometimes there may be a void in the matrix, and the presence of void leads to what happens is that if we do not consider the void presence of void, and if the volume of the void is not negligible, in that case the density calculated theoretically without considering the void volume will be definitely different from the density which is actually measured experimentally. Okay. And in addition to that, the presence of void results in degradation of some of the matrix dominated properties like shear stiffness and shear strength, compressive strength, transverse tensile strength, fatigue resistance and moisture resistance of the composites. Okay. And it is reported that presence of for each 1% increase in the void content, sometimes the degradation of these matrix dominated properties is as high as 10%, it varies between 2 to 10%. Okay. Therefore, if the void volume is not negligible, in that case it should be taken into account in the analysis of the micromechanical analysis of the composites. Okay. So, therefore, we need to find out what is the void volume fraction. So, analogous to the fiber and matrix volume fraction, we could define the void volume fraction as the ratio of the void volume to the volume of the composite. Okay. What the total volume of the composite is V c is equal to V f plus V m plus V a v. We have already done that in earlier case, we neglected this volume of the void. Now, if we consider the volume of the void, therefore, if the experimentally measured density is suppose rho c c, then the mass per unit volume going by the definition of density. So, V c is the total volume considering the void volume is mass of the composite W c divided by the volume of the density of the composite rho c c. On the other hand, in the theoretical density is rho c t, that means where we do not consider the volume of the void, then this volume of the composite V c is equal to mass of the composite rho c divided by the theoretical density, and this V c, in this V c we did not consider the volume of the void. Therefore, from these two expressions we could find out, we could write that volume of the void V b is nothing but this minus this. Now, please note that in this case the W c is same whether we have considered void volume or not, weight is same, meaning that we have actually neglected the weight of the void. So, we get an expression finally that we get a relation where the void volume fraction V v could be related to the theoretical density and experimentally measured density. Okay. Now, so we understood some of the important terminologies like the volume fraction of the fiber, volume fraction of the matrix. Of course, they are dependent, knowing one we could find out the other because V f plus V m is equal to 1. So, how to determine the volume fraction? Suppose we have a lamina, we want to determine what is the volume fraction of the fiber. Okay. So, this could be determined using burning or dissolving the lamina in the acid. What is done is first a sample of the lamina is weighed and we find out what is the weight W c, okay, of the lamina. Then the density of the composite is actually measured by liquid displacement method. We know how to find out the density by liquid displacement method. First we take the weight of the composite in air and then weight of the composite immersed in water, and then using this we know the density of water. Therefore, we can find out what is the density of the composite rho c. So, once the density is determined, I mean suppose the composite is light and it does not sink in the water. Therefore, in order to determine its weight in the water, we provide a sinker and weight of the sinker is actually taken into account while finding out density using this formula. Okay. Then once the density is determined, we burn the composite. In burning, it is only left with the fibers or it is dissolved in acid. So, that only the fibers are left out. Then the fibers are weighed and we find out what is the weight of the fiber W f. Therefore, we know what is the weight of the matrix, and from these relations we can find out what is the volume fraction of the fiber, we could find out what is the volume fraction of the matrix. That is how, given a sample lamina, suppose we want to find out what is the volume, what are the volume fractions, we could actually determine that what is the volume fraction of the fiber in the lamina. Now, in micromechanics, representative volume element is an important concept. Okay. What is representative volume element? Actually, it is the smallest region representing the lamina by material sand is constituted volume. That means, we choose a small region from the lamina such that that particular region, that particular piece of volume actually represents the lamina by its material. That means, it consists of both fiber and the matrix. Not only it consists of both fiber and the matrix, it actually represents the true volume fraction. Suppose the overall volume fraction of the lamina is 60%, therefore, the representative volume must be such that the fiber volume to the volume of the representative volume is actually 60%. Now, choice of scales of the volume is very important, okay, because it must truly represent the lamina. Many a times one single fiber surrounded by matrix does the purpose, but many a times also more than one fibers are required depending upon how regularly the fibers are spaced. Fiber spacing and lamina thickness are important dimensions in a representative volume element. Okay. So, in the case of a lamina, you can see this is the representative volume. Suppose this is a lamina where the fibers are equally spaced. Okay. Suppose in the thickness direction, you can see all the layers are similar. Okay. The fibers are equally spaced and are distributed also uniformly across the thickness direction also. Therefore, we can take only one fiber surrounded by matrix, such that the ratio of the volume of the fiber to the volume of the matrix actually represents the volume fraction of the lamina. Now, it is further simplified by considering fiber which is actually circular cross section, by considering this fiber to be of rectangular cross section instead of circular. Here we have considered this to be rectangular without actually changing the volume fraction. That means, we choose the fiber cross section as rectangular, but then the volume fraction remains the same. Therefore, in such a simplified representative volume element where the fibers are continuous, therefore, the length of the fiber, length of the matrix and length of the composite is same. Okay. Height of the fiber, height of the composite and height of the matrix is also same. So, in this simplified representative volume element, this shows the simplified representative volume element where Tf is the width of the fiber, Tm is the width of the matrix. Okay. Tf is the width of the fiber, Tm is that of the matrix, and Tc is the width of the composite. Of course, this is equal to Tm plus Tf. Okay. And here, because we have taken a simplified representative volume element, therefore, the height of the fiber Hf, height of the matrix and height of the composite is same, which is equal to H. And because the fiber is continuous and parallel fibers, therefore, the length of the fiber, length of the matrix and length of the composite is same, and which is L here. And the cross sectional area of the fiber is this Tf into H, cross sectional area of the matrix is Tm into H, and the cross sectional area of the composite is Tc into H. So, the volume fraction in such a simplified representative volume element could actually be expressed, it is Vf by Vc. However, because the length and height are same, therefore, the volume fraction could as well be represented by the ratio of the width of the fiber to the width of the composite Tf by Tc, or area of the fiber to the area of the composite. Okay. So, having understood the volume fraction and the representative element, okay. So, irrespective of what are the approaches of used in micromechanical analysis, there are certain key assumptions which are actually made in micromechanical analysis. Perfect bonding between the fibers and the matrix, elastic moduli, diameter and space between the fibers are uniform, fibers are homogeneous, continuous and parallel, fibers matrix are isotropic and follow Hooke's law, fibers possess uniform strength and composite is free from void. Each of these assumptions have certain reasonings. Perfect bonding means once the lamina is loaded, it means that at any point of time the lamina when the lamina is loaded, fibers and matrix do not get debonded from each other. That means, if the fibers and the matrix get separated, that means there is a fracture at the interface that is not desirable. So, we assume perfect bonding. Okay. Then elastic moduli, diameter, space between the fibers are uniform, that means fibers are uniformly spaced, all the fibers are of the same material, okay, same size and shape. Okay. Of course, fibers are single material homogeneous, they are continuous, no fibers are broken and they are parallel. Okay. And fibers are isotropic, matrix are also isotropics and they are linearly elastic, therefore, they obey Hooke's law. Okay. the strength of the fibers are uniform, all the fibers are of uniform strength, which may not be true actually. When you have large number of fibers, the strengths actually vary statistically, but we assume here that the fibers are of uniform strength, and as already mentioned, we consider the composite to be free from voids. If there are very small number of voids, this is a reasonable assumption. However, if the voids are significant, which may be because of the manufacturing defects, then we have to consider voids as we have seen just now. Okay. Now, having understood this micromechanics and the approaches and the key assumptions in micromechanics, let us try to see how some of these stiffnesses and strengths are actually determined using micromechanics. So, let us start with mechanics of material approach, and which is the most simple among all these approaches. So, let us see the determination of longitudinal Young's modulus E1 using mechanics of material approach. We consider an RV, okay, where this RV is already discussed. So, where we apply a load along material direction, principal material direction, that is the longitudinal direction 1. Okay. F c is the load applied along direction 1. Okay. Now, all the assumptions are already there. Just now we have mentioned number of assumptions, all assumptions are there for this analysis. Okay. So, if F c is the total load applied along direction 1, because it consists of fibers and the matrix, the load will be shared by the fiber and the matrix. Suppose F f is the load share of the matrix and F m is the F f is the load share of the fiber, F m is the load share of the matrix, and suppose because of this load F c, the stress in the composite is sigma c. Of course, sigma c is nothing but F c divided by the cross sectional area. In this case, you can see the cross sectional area is T c into H. Similarly, if sigma f is the stress in the fiber, so this is F f divided by A f. A f is nothing but, in this case it is T f into H. Similarly, stress in the matrix sigma m is nothing but F m divided by A m. A m is nothing but T m into H. Okay. So, naturally F c is equal to F f plus F m, that means the total load in the composite in the lamina is actually shared by the fiber and the matrix. Okay. Now, as we have just now discussed that F c is nothing but sigma c into A c, and F m is nothing but sigma m A m, and F f is nothing but sigma f into A f. Therefore, we put this and we get this expression. Okay. So, another assumption is that this both fiber matrix and the lamina, they obey Hooke's law. Therefore, if sigma c is the strain in the lamina, then because it follows Hooke's law, it must be, if epsilon c is the strain in the lamina, epsilon c is equal to sigma c by E c, where E c is the Young's modulus of the composite. Okay. Similarly, for the fiber, the strain along 1 is nothing but the stress in the fiber sigma f divided by the Young's modulus of the fiber. Again, the matrix also follows Hooke's law. Therefore, epsilon m is equal to stress in the matrix sigma m divided by Young's modulus of the matrix E m. And when we put this, so we can write sigma c in terms of strain and Young's modulus, sigma f in terms of strain and Young's modulus, sigma m in terms of strain and Young's modulus, and we get these expressions. Okay. Now, we assume here that there is a perfect bonding, and therefore, the strain in the fiber, strain in the matrix and strain in the composites are same, meaning that because we have applied a load F c along direction 1, under this load the extension along 1 is same in the matrix, fiber and composites. Okay. That means, they extend by the same amount along direction 1, delta c is equal to delta f is equal to delta m. Now, because their initial length is also same, it is L, therefore, the strains are same. So, what does it mean? Suppose they are not same, it means if they are not same, if the composite if the fiber and the matrix do not experience the same strain, that means there is a fracture at the interface of the fiber and the matrix. Okay. So, we assume a perfect bonding which leads to uniform and same strain in the fiber matrix and the composites. Therefore, we can neglect therefore, we can remove this sigma c, sigma f and sorry epsilon c, epsilon f and epsilon m, they are same, and we get that E c is equal to, dividing both side by A c, E c is equal to E f A f by A c, E m A m by A c, and we have already discussed that for the simplified representative volume element, A f by A c is nothing but the volume fraction of the fiber, A m by A c is nothing but the volume fraction of the matrix. Therefore, we get E f E 1, E c is nothing but in this case the Young's modulus of the composite along direction 1, because the load is applied along direction 1 in this case. Therefore, E 1 is equal to E f V f plus E m V m. So, we could establish a relation between the longitudinal Young's modulus in terms of the Young's modulus of the fiber, Young's modulus of the matrix and their relative proportions, and it could be clearly seen that as the volume fraction increases, E 1 increases. Okay. Now, you will appreciate one thing here, that in general the Young's modulus of fiber is far higher compared to that of the matrix. Okay. So, therefore, change in Young's modulus of the matrix does not have much influence on E 1. Okay. Change in Young's modulus of the matrix actually insignificant in terms of E 1 until or unless the volume fraction is very near to 0. Okay. Therefore, E m does not influence E 1 until, okay. Therefore, E 1 is actually a fiber dominated property. Therefore, longitudinal Young's modulus is actually fiber dominated property. Okay. Now, what is the, now given a load applied along 1 in a lamina, what is the proportion of the load that is carried by the fiber? Now, fibers are very strong and stiff. Therefore, if we see that what is the proportion of the load carried by the fiber to the load carried total load F f by F c, we can see that it is a function of E f by E c and the volume fraction. Naturally, for a given modulus of fiber, given Young's modulus of fiber, if the volume fraction is more, the more load is carried by the fibers. Say in the extreme case, if all fibers are there, all the loads are carried by the fibers only. Therefore, we can write this F f by F c in terms of E f, E m and V f. So, this is what is the proportion of load that is carried by the fiber, and it is a function of E f, E m and V f, and for a given ratio of E f by m, it increases with V f. Okay. As E f increases, that means Young's modulus fiber is more, the more load is carried by the fibers, and for a given Young's modulus of the fiber, if as the volume fraction increases, the load carrying the proportion of the load carried by the fiber increases with V f. So, this is how it shows. With increased E f by m, the load carrying capacity of the fiber increases, and for a given E f by m, as the volume fraction increases, the load carrying capacity of the, not the load carrying capacity, that the proportion of the load carried by the fiber is increases with the increase in volume fraction. Now, determination of transverse Young's modulus using mechanics of material approach. Same representative volume elements we have taken here also, but only thing is that here the load is applied along direction 2, that means it is the transverse direction. Okay. All others are, the representative volume remains same. Okay. So, subjected to a load along direction 2, the load is applied along direction 2. Therefore, suppose the corresponding strains epsilon c is the strain in the composite, epsilon f is the strain in the fiber, epsilon m is the strain in the matrix along direction 2. Okay. And say the stress corresponding stresses in the composite, fiber and matrix because of this load along direction 2 are sigma c, sigma f, sigma m, and say capital delta C, capital delta F and capital delta M are the extension. We apply a tensile load along 2, therefore, the extension in the directions for the composites, fiber and the matrix are delta C, delta F and delta M, and E C, E F, E C is the Young's modulus of the lamina along of the composite along direction 2, E F is the Young's modulus of the fiber, E M is the Young's modulus of the matrix. Okay. Now, naturally I mean, so we write here that the total deformation along 2 is nothing but the deformation of the fiber plus deformation of the matrix. That means, the extension along direction 2 because of the load F is contributed by what is the extension of the fiber and the matrix. Okay. So, now we can write that because it is loaded in the direction 2. So, and epsilon c is the strain. Okay. So, by the definition of the strain along direction 2, strain along direction 2 of the composite is nothing but the change in length by the initial length. Okay. Similarly, for the fiber it is the change in length delta f, that means, the extension along direction 2 to the initial length. Similarly, for the matrix it is change in length along direction 2 by the initial length along direction 2. Okay. So, we can write this as epsilon c, I mean delta c is equal to epsilon c T c. So, similarly, delta f is epsilon T f, delta m is epsilon T m. Now, again the assumption that fiber, matrix and the composites all obey actually Hooke's law. Therefore, this epsilon c is nothing but sigma c, the stress by the Young's modulus. Similarly, here it is epsilon f by sigma f by E f, and this is sigma m by E m. Stress by strain is the definition of Young's modulus. Therefore, we use this here and we can write like this. Okay. Epsilon c is equal to sigma c by E c. Similarly, epsilon f and epsilon m could be written as sigma f by f and sigma m by m. Okay. Now, along direction 2, the stresses are considered to be equal. Try to understand what exactly this means. This was the RV, okay, and it was, this is the load which was applied. Now, this is the fiber and the rest is matrix, this matrix, this fiber. Okay. What is the stress along direction 2? Whether you consider matrix or you consider this or you consider this, the area resisting this force is same. Therefore, stress in the matrix, stress in the fiber and the stress in the composite is same. Okay. Therefore, sigma c is equal to sigma f is equal to sigma m. Okay. Stress in the direction 2 is same, but unlike in the longitudinal Young's modulus, here we did not make any assumption in direction 1, okay, but in direction 2 the stresses are same. Okay. Whereas, in the case of longitudinal Young's modulus, determination of longitudinal Young's modulus, we made an assumption that the strains in direction 1 were same. This is reasonable only when the fibers are perfectly spaced. That means, this particular cross section contains fibers only here, okay, and suppose the fibers are also not regularly spaced along the thickness, in that case it will not be same. Okay. If the fibers are also not regularly spaced along the thickness, it will not be same, then the stresses will be shared by the fiber and the matrix. However, for the given representative volume, this assumption is fine, sigma c is equal to sigma f is equal to sigma m. Now, putting this in this, so we get 1 by E c is equal to 1 by E f T f by T c, 1 by m T m by T c, and for the given volume fraction for the given representative volume element, we know that T f by T c represents the volume fraction. Therefore, we get 1 by E 2 is equal to V f by E f plus V m by E m. Okay. Now, this E c is nothing but E 2, because this is the Young's modulus of the lamina in the direction 2. Okay. So, using mechanics of material approach, we could establish the relationship where the longitudinal Young's modulus and transverse Young's modulus of the lamina could be expressed in terms of the Young's modulus of the fiber and the matrix and the relative proportions. Okay. Now, we could see that say in case of longitudinal Young's modulus, that as volume fraction increases, U1 increases. So, what could be the volume fraction? There is an upper bound. I mean, there are practical limitations on the maximum value of volume fraction. Now, depending upon the packing, depending upon the arrangement of the fibers, suppose the fibers are regularly spaced in a square array. In this case, suppose in a square array where this S is the fiber spacing and this D is the diameter of the fiber. This is one full fiber, this is the diameter of the fiber. Okay. So, in a square array, I mean considering an RV where length of the fiber, length of the matrix and the length of the composites are same, therefore, the volume fraction here is pi by 4 d square, that means, it is the area of the fiber total, there is one fiber and A square is the area of the square, therefore, the volume fraction is given by this. Okay. Now, the maximum volume fraction will be attained when these two fibers touch each other, that means, when the fibers are packed like this, okay, which means that D is equal to S. If we put D is equal to S, we get the maximum volume fraction that is possible is 78.54% in case of the fibers arranged in a square array. Okay. Similarly, in the case of an hexagonal array, we could find out that the limit is that D is equal to S when the fibers touch each other, and we could see that the maximum volume fraction that is possible is 90.69%. However, it is not possible to I mean, it is not possible to realize this kind of volume fraction, because the fibers touching each other means that that there is not sufficient weighting of the fibers, and because the matrix actually binds the fibers. Okay. Therefore, if the fibers touch each other, so there will not be sufficient weighting, and therefore, this cannot be used as a structural element. Okay. Therefore, this high volume fraction could not be obtained. This is the theoretical maximum which is possible. Say for example, suppose square shape fibers in square array. I mean, this is not to scale, but suppose this is a square shape fibers in square array. Okay. Then the volume fraction could be as well equal to 1, that means, there is no matrix, but this is not possible. So, similarly, there are practical limitations on the maximum volume fraction of the fibers. So, we will stop here today. Next class we will see further discussions on this determination of these stiffnesses using mechanics of material approach in micromechanical analysis of lamina. Thank you.